Hello again. We have two more videos in this standard. That's my plan at this point. I want to talk to you today about solving exponential functions for the input variable. So most times that's our x in the exponent. How do we solve an equation when we're given the y and need to find the x? That's a level 2 skill that you'll just need to show for level 2, but you'll have to apply it in level 3 for any word problems necessary. And then the other video that I want to do for Wednesday is going to be about the rule of 70. So those are kind of the last two things to do. You guys are getting a lot of practice here on exponential functions, so keep working hard. What I actually want to start with in order to talk to you about solving exponential functions for that input today is actually go over and start with this number 17 that you did in yesterday's homework. All right. So if you don't remember that, the question says a pollutant was dumped into a lake and each year its amount in the lake is reduced by 25%. So A, we need to construct a general formula, and B, we need to answer the question, how long will it take before the pollution is reduced to below 1% of its original level? So part B kind of addresses the next thing that I want to teach you. So I just thought this would be a good one to go over. So first off, this is that idea of they're giving us the terminology of a rate in a percentage. So if the amount is being reduced by 25% every year, what we can do is we can first think about, all right, we're starting with this a sub 0 amount. That's our initial value. We don't know how much that is, but we're going to use a sub 0 to represent that. I'm calling it P for pollution of n. N is the number of years. A sub 0 is our initial amount. And then what do we put in for our decay factor when they say 25% it's reduced by 25% every year? Well, hopefully from yesterday we recognize that means our decay factor is 0.75, 1 minus 25%. There it is. Now, so that's part A. Hopefully that was okay for you. Part B, though, says how long will it take, in other words, what is our n? We need to solve for n until this value becomes 1% of what you started with, all right? Now you might say, well, since we don't know how much we started with, we can't figure it out. But we actually don't need to know how much we started with because they're just giving us this percent, I should say, is enough. So we can replace P of n with 0.01 of a sub 0. So just this little product, okay, that means whatever a sub 0 is, this is going to be 1% of that. That's what we want. We want to find n when that's happening. So I'm just substituting that in for the y. And now we're going to solve for n. Okay, so up till now, you would do this by simply probably making some kind of table, right, where this is a sub 0, or sorry, this is n, and this is your p of n, right? And maybe you picked out some a sub 0, and you just kind of kept, you picked out a random number, maybe it was like 100, right? So when n was 0, this started out as 100, okay? When it was 1, then you were down to 75. When it was 2, and you could just keep working down until you got to how far do you have to go until you get to, in this case, 1, because that would be 1% of 100. Okay, so I just made up that 100, but this is one way you could think of it based on your current skills. But what I'm showing you now is a new way, more of an algebraic way of solving this. This actually is from lesson 6.1. That's where you're going to be doing some of this work for your homework tonight, lesson 6.1. But let me continue on with this. So here's what we got. We talked about why this should be 0.01 a sub 0. We're solving for n. So how do we get n by itself? Well, the first thing you're going to have to do is you're going to have to divide by this initial value. And notice, cancels out over here, obviously. Notice over here, it also cancels out. That's why I said initially it didn't matter what our actual number we chose was, as long as we know the percent. So there's our 1% equals 0.75 to the n power. So how many n's does it take for this decay factor to essentially be 0.01? To do this now, this is the new thing. So there is a logarithm rule that comes in to help us solve this. If we take the log of both sides, okay, we can get away with that because our algebra rules say whatever you do to one side, if you do it to the other, it stays balanced. Okay, but there's a log rule that applies right here that says any exponent can be pulled down to the front like this. Okay, so that n, we can take it down and put it as basically like a coefficient in front of that logarithm, 0.75. And notice that makes our lives easier now. So the log of 0.75 is just a number. Don't forget about what we learned last standard. That's just a number. It's an exponent, remember. So we're gonna divide both sides. Kind of running out of room here. So we had log 0.01 equals n times log 0.75. I'm going to divide both sides by that log of 0.75. Okay. Those go away there, leaving you with n on this side. And this is what you're going to divide in your calculator. Just type that in, and it comes out to 16.008, right? So approximately 16, what was our label here? Yeah, we were talking years, right? I lost my place. Each year, yep. So approximately 16 years before that pollutant is at 1% in the lake. Okay, so that's the process. I'm going to show you one other example. And that'll be that. So I'm actually going to have you turn to lesson 6.1 for this example. I'm going to be doing number 24 on page 356. To save some time on the video, please take a look at that, read that through yourself right now before you start in on it. Okay, but I'm going to go through it now. Hopefully you paused it and read it. They want us to construct an exponential model for per capita whole milk consumption in gallons. So this is something we've already done. They talk about the decrease as a percentage, so we know it's going to be a decay. So we have m of t equal to the initial amount consumed by each person was 27.4 gallons. And the decay rate is 3.9%, which corresponds to 0.961, I believe 0.961, and then to the t. So that's what you got done doing yesterday for homework. Hopefully that part's okay. Now part B says, use your model to estimate the year in which the per capita whole milk consumption dropped to 6 gallons per person. So we have to recognize what they're giving us in terms of 6 gallons. What variable goes with that? Emily, do you want to say hi? All right. What is that variable representing? Is it a time, or is it, in this case, number of gallons of milk? And so obviously in this case it's gallons per milk. It goes in for m of t. And so we just substitute that in there. And now we use the process that I just showed you on the last one. We're going to get rid of this initial value by dividing both sides by it. And when you divide that, you are left with 0.219. These cancel out, 0.961 to the t. Now this is where we take the log of both sides. That t moves down in front. That's the log rule. You'll see that in lesson 6.1 when you read that chapter or that lesson. So it gets you to there. Then you're going to divide both sides by log 0.961. Sorry, it's getting kind of small and messy. Okay. And when you type that into your calculator, you come up with 38.2 years. Now you're going to have to be a little discerning with an answer. Make sure it answers the question. They're asking us in what year will it have dropped to that? Well, we have to recognize that's not telling us a year. We have to know that, okay, this model started in the year 1970. This is how many years after 1970 we're going to be at 6 gallons per person. So we have to add that to 1970, which takes us to approximately the year 2008. So our answer would be the year 2008 in part B. That's all I got for you today. Thanks for listening. Keep working hard. See ya.